Lots of people getting here on time. It's a shame. All right, so today we're starting chapter 4. This is not on your test on Tuesday, but we need to keep going. So 4.1, we are looking at increasing and decreasing functions. And something called concavity. So let's say we've got a nice little XY domain region plane. That's the word I'm looking for. It's a plane. And we've got a nice little curve here. And at some point, it just flattens out. Say this is 1, 2, 6, 10. And if we're looking for regions that are increasing, I'll give you a second to draw it. That way you're following along. All right. So if we're looking at regions of increasing, it looks like it's increasing all along this path. And so we could say it's increasing from negative infinity to 2. And then along here as well, from 6 to 10. We have the function is decreasing. Well, it looks like it's going downward between 2 and 6. And then regions where it's constant, where it's neither increasing or decreasing, 10 to infinity. So we're going to do a little stuff with this graph, but now we've been doing calculus. This is a calculus course. So how does calculus connect to looking at these regions of increasing and decreasing? Well, let's take a look at the regions of increase. What's going on with the slope if we look at the regions of increase? The slope is the tangent line at a point. It looks like everywhere that the region's increasing, m is greater than 0. And if m is greater than 0, that means f prime of x is greater than 0. We notice something similar with decreasing regions. The tangent line is pointed downward. So m is less than 0, which means f prime of x is less than 0. And our constant regions, tangent line is literally just the same thing. It's flat. So the slope for a constant region is m equals 0, which means f prime of x equals 0. And this gives us, rather than having a graph sheet, rather than having a graph, we now have a way of testing we can find regions of increase and decrease without graphing. So you did increasing and decreasing, presumably in college algebra, or if you had that at high school algebra. Hopefully they covered looking at increasing and decreasing regions. Now we have another means of doing it, which I'm going to write on the next page. So Dalton, you guys, or anyone that just walked in didn't miss it. Does anyone need this up longer? Let me let you take a picture. All right, so now we get to our test for increasing, decreasing, and constant. One, if f prime of x is greater than 0 on AB, the interval AB, then f is increasing on AB. Two, if f prime of x is less than 0 on AB, then f is decreasing on AB. And finally, if f prime of x equals 0 on AB, on an interval AB, B, then f is constant on that interval. Take a look at an example. Without graphing, find the regions of increasing and decreasing for f of x equals x squared minus 5x plus 6. So if we take the derivative, what do we get? 2x minus 5. All right, well, what can we do with that? Well, we want to find out where it's greater than 0 or less than 0, so it might help to find where it equals 0. So we'll set that equal to 0. And we get x equals 5 halves, which is 2.5. And now this is usually easiest to do if you make a sign chart. So put your values on there that you found. Here we found 2.5. And use test points to the left or the right. I will try 0 and 5. I plug in 0, I've got 2 times 0 minus 5. That is negative 5. So this whole region is, negative. If I stick in 5, we're plugging them into f prime of x. If I stick in 5, I have 2 times 5 minus 5 equals 5. So everything to the right of that is going to be positive. So f prime of x is less than 0 on negative infinity to 5 halves. And f prime of x is greater than 0 on 5 halves to infinity. We can verify that. F of x equals x squared minus 5x plus 6. Couple ways you could do it. We could factor it. We get x minus 3, x minus 2. Which shows that it crosses 0 here and here. We know it's a parabola, so it opens upward. And the vertex is going to be between them. And halfway between 2 and 3 is 2.5. I didn't calculate what the y value is, but I know it opens upward, so it's got to be below the graph. Any questions so far? So it's really easy to find regions for increasing and decreasing. You just take the derivative, set equal to 0 to find your important points. They're called critical points. And do a sign chart to check regions. What about the second rig? What does the second derivative measure? What does it measure on a graph? It's the change in the slope, right? So if the second derivative is greater than 0, that means the slope is increasing. Yeah, we're getting to that. That's what this topic is next. Ainsley posted it and deleted it like a ninja. I saw it up there. Just fucking vanished. So like we could have it starting at a flat point, and then as we go to the right, it's slowly going up. It's getting steeper. But that's not the only way shit increases. It could be really steep coming down from the left, and it gets less steep. So like this could be m equals -3, -2, -1, 0. 1, 2, 3, and 4. Yeah, I said your name again. I used your real name. How dare I? Voldemorta had the answer. If it's less than 0, our slope is decreasing. So it could be really steep and then just flatten out and do some shit like that. So I could be going like the other way. 3, 2, 1, 0, -1, -2, -3. As we go from left to right, the slope is getting more and more, or it's decreasing, it's going negative. This is called concavity. Where the slope is increasing, this is called concave up. And where the slope is decreasing, this is called concave down. I picture it like a cup. Which way does the cup open? Opens up. Or the cup could be going downward. Yeah. And like this is my graph part that I'm looking at. So looking at that function we did up there, we had f prime of x equal 2x minus 5. And the second derivative was just 2. Which means it's concave up everywhere. Okay, just writing that down. Anyone need that longer? Okay. So let's do f of x equals 3x to the 4th power minus 2x cubed. and take a few minutes to find intervals for A, increasing, decreasing, constant, and B, concavity. Pause the video for a second while you guys work on this. Before I do this, I want to show you guys an announcement I just put up. We are doing a Python boot camp this weekend. It's sponsored by UC Berkeley. It's Saturday and Sunday. It's at the Mesa Center from 10 a.m. to 1, both days. If you have a laptop and are interested, there's a little flyer. I'm going to be leading it. I'm going to have my laptop hooked up. They're doing it over Zoom. I'm going to have my laptop hooked up, projecting the information on big screen. And then I'm going to have my another computer with me to do it. If you're interested, there's a little QR code you can register at and information on what you'll need to install before then. Again, this is in the John Muir building over in by Saturday and Sunday morning. They're doing, it's different topics both days. So if you're doing it, you might want to show up for both. If you're interested in computer science, this is learning how to program with Python, which is not a class we teach at COS. We teach C++. And that's in the announcements. You can see it there. All right, what do our derivatives give us? What's the first derivative?
X cubed minus 6x squared.
12x cubed minus 6x squared. That looks pretty good to me. That looks about right. If I set this equal to 0, we can find the regions that we're looking for. I can factor out a 6x squared. And I'm left with 2x minus 1 equals 0. This should give me points x equals what? Wait, someone's got an answer. Let's follow.
Okay.
What?
It's 0.
It is 0 and 1/2. Most people get the 1/2. A lot of people miss the 0. Don't forget this one. So we've got, let's see what we got. Doesn't give us a lot of room to check, does it? So that's like 0.5. So maybe we do like 0.25 in the middle. Maybe -10, +10. These are our regions, 0 and 1/2. If I plug in -10, the x squared becomes a positive. So if I'm just checking for signs, I don't actually need the value. So 6 times -10 squared, and then 2 times -10 would be -20 minus 1. Negative 10 squared is positive and negative 20 minus 1 is negative. When I multiply them together, this region is negative. With that in mind, while 0.25 may have sounded like a bitch to deal with plugging in, I just need to know if it's positive or negative. The 6 is always positive, so 0.25 squared, that's positive. And 2 times 1/4 minus 1, that's negative. So that's negative as well. And if I stick in positive 10, both of those things are positive, so this is a positive region. So it's increasing from 1/2 to infinity. And it's decreasing from negative infinity to 1/2. Now we take a look at concavity. What do you mean, Isaac? We don't need to actually factor this one up here. Factoring f prime of x helped. Helped us find the regions. Well, oh, it's a question. Okay. Well, we needed to find the critical points where the sign might change. And the easiest way to do that is using the zero product rule by factoring. Okay. Next question is concavity. So we had f prime of x was 12x cubed minus 6x squared. So f double prime. Ooh, 36x squared minus 12x. Well, it is what it is. Again, having a sign chart will be pretty helpful. So we're going to set it equal to 0 and factor. Both of those numbers are divisible by 12 and x. And that should leave a 3x minus 1. So my critical points are x equals 0 and x equals 1/3. Do our little sign chart. Getting even a smaller window here, aren't we? Halfway between 1/3 and 0 is 1/6. And we can do negative 10 again. And and positive 10. So if I stick in -10, the 12 is always positive, so I'm not going to worry about that check for my derivative. Don't need that for this sign check. -10 is negative, and 3 times -10 minus 1 is also negative. A negative times a negative is a positive, which means this region is positive. Oops. When I check 1/6, I've got my x, that's 1/6, that's positive. And then I've got 3 times 1/6 minus 1. This is 1/2 minus 1. And that's a negative. So I've got a positive and a negative. This region is negative. And when I try 10, I've got 10, and then 3 times 10 minus 1. That's 10 and 29. They're both positive, so this region is positive. So we have concave up, wherever that was positive. Negative infinity to 0 in union with 1/3 to infinity. And we have concave down between there, 0 to 1/3. So another little piece of information to go with this. If f is continuous, and polynomials are continuous, so this was a continuous function. Then wherever the concavity changes, it's called an inflection point. So a handy way of just looking at this is, where does f prime of x change signs? Not f prime, double prime. So we actually had both points we came up with earlier, x equals 0, x equals 1/3, are inflection points for what we had. Any questions? So we're gonna do more with this function in just a second. In fact, I'm gonna use it as a segue to 4.2. But I do want to show a little bit more in this area before we segue, and we'll take a break too. But let's point out there's lots of combinations here. Many combinations of how this goes. If f prime of x is increasing, but f double prime of x is decreasing. So we have an increase, but concave down. It's got to be doing something like that. And then if f prime of x is increasing, but f double prime is also increasing. So we've got increasing and up. It's got to be looking like that. And we could do our downward ones, our decreasing regions. F double or f prime of x is less than 0, so it's decreasing. And f double prime of x is also less than 0, so it's downward. So it's got, the cup has got to face down and the slope has got to be going down also. So that's doing something like this. And then we could look at f prime of x is less than 0, but f double prime of x is greater than 0. So it's decreasing, but concave up. So it's got to make an open cup, but it's going downward. So it's doing something like that. So if we have something like this, right here, the concavity changes. The tangent line actually goes through it. So this is an inflection point. There's other setups where this doesn't work though. Like if I had something like this, so it's concave up and then all of a sudden it was concave down. So concave up, concave down. That's not an inflection point though. The reason why is it's based on derivatives, and the derivative doesn't work here. Remember, derivatives are based on the slopes. And the slope needs to be continuously changing. Here, the slope is negative, and all of a sudden it's drastically positive, and there's no gradual change. So the limit for the slope coming inward is not the same for both sides. We could also have a sideways graph that does something like this, where the tangent line here, the concavity looks like it's changing there. Well, the concavity is changing there, but like the derivative doesn't exist here either. Because slope is undefined. It's a vertical line. Let's take a 5-minute break. All right, so we're going to switch over to doing 4.2. I did want to point out something before I did. For your test coming up, 6.9 had the hyperbolic functions. And I told you I wouldn't test you on the derivatives or anything, but I do have to give you something in there. So for the test, be comfortable with cosh x equals e to the x plus e to the negative x over 2, and sinh x equals e to the x minus e to the negative x over 2. And you're going to have a little like prove one of the trig functions, one of the hyperbolic trig identities. We did an example in the lecture notes. You can see what I'm talking about, how to do it. You have something like that on there. I didn't put any derivatives for the hyperbolic inverses or any hyperbolic functions on there, but there's something on there for this. And you guys, this was 6.9. We did it right in the middle of chapter 3. 3? 3. We only got 2 chapters left. Chapter 4 is a long one. Chapter 5 is, chapter 5 is the good stuff. The other good stuff. Derivatives are the good stuff. Chapter 5 is the other good stuff. All right, so we had f of x equals 3x to the 4th minus 2x cubed. If I had said that equal to 0, I got x cubed times 3x minus 2 equals 0. I have roots at x equals 0 and x equals 2/3. We showed we were increasing from 1/2 to infinity, decreasing from negative infinity to 1/2. What else did we have? we had concave up. I'll say call it CU. Negative infinity to 0 in union with 1/3 to infinity. And concave down was between those 0 to 1/3. Now, without doing a y-axis here, we can get a good idea of what the graph looks like. I have 0. A lot of shit's going on between 0 and 1. So that's 1/2. That's 1/3. That's 2/3. 1/6, 5/6. And actually, if I plug in x equals 0, f of x equals 0. So I could put it y-axis here. I'm just not going to find out where everything changes things. We're going to do just a little quick sketch of what's going on. We know it crosses, the graph crosses at 0 and it crosses at 2/3. We know it's concave down from 0 to 1/3. So we'll have like something like that in here. And it's still increasing right there. So on 0 to 1/3, it's in. No, it isn't. It's decreasing there. 0 to 1/3, it's decreasing and it's concave up. Nope, concave down. So it's like that. It's got to be doing something like that. And then went from 1/3 to infinity, it's concave up. But it's still decreasing to 1/2. So it's got to be doing something like that to the 1/2 mark. And then it's got to be going concave up. And it looks like from 0, let's see. It's decreasing all the way from infinity. So it's coming down. So if I wanted to get a good idea of what's going on here, from 0 to 1/3, it's concave down and decreasing, and I know it passes through 0. So if it's going downward, it's got to be doing something like that. And it's still decreasing all the way up to 1/2, but the concavity changes and it starts going upward here. And at 1/2, the concavity is still up, but the slope starts increasing. So it's got to be curving like this. And the concavity is to the left of that, left of 0. It is concave up, but decreasing. So it's like that. Now, without having the y values of seeing where some of this happens, we can get a sketch of what's going on with the graph just by looking at increasing and decreasing slopes and concavity. actually was not a good graph to segue into 4.2. So we're going to be doing curve sketching throughout this chapter. More on it in 4.3 and 4.4. 4.2 is on something called a relative extrema. Does anyone need that up longer? Extrema is plural for extremum. And extremums are maximums and minimums. Because that doesn't have an apostrophe there. So a relative max means that in a small region, around the point, x naught, f of x naught is greater than every other value. So we're looking at small regions of the graph where shit changes. Where things have a maximum value and a minimum value. I'm going to call this point, that's x1, this is x2, this is x3, that's x4. And with the graph keep going on, we're just going to talk about those regions for now. We have a relative max. If I put a small window around each of these. Oh. We're looking at a small interval around each of them. At x2, f of x2 is greater than everything around it. And f of x4 is greater than everything around it. So this is a relative max, and so is f of x4. Our other relative points are these two. And those have the lowest value in the region around them. So these are relative mins. God damn it. We keep hitting the button. X1 and X3 are relative mittens. So relative min says the same stuff. Blah, 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 blah. F of X naught is less than every other value. In the local region. And together, these are called their relative extrema. Ready for more? All right, so where do they occur? These critical points I'll call them xi for a function f. Occur for values of x, I in the domain. It's got to be in the domain. Where, whoa, what the fuck? Lamp just went crazy. Okay. Oh my God, that's hella bright. Now it's too dark. Where f prime of, well, a couple options. A, f prime of x equals 0. Or B, f prime of x does not exist. And we saw that with our graph right here. The derivative exists here, but it doesn't exist here. These three have tangent lines that are horizontal. But we don't have a tangent line here. Okay. To distinguish between these 2 points, we call these called stationary points. That helps distinguish between them, but they're both like critical in doing this. So there's a fun theorem. If F has a relative extrema at x naught, then x naught is a critical value of f. Maybe I'll put f of x, because that looks like the word off. Ah, fuck it. Just move to the next line. This is not a two-way street. If we say it the converse way, if x naught is a critical value, then it may or may not a relative extrema. There are where this occurs, like if I have something like this, f prime of x does not exist here. But it's not an extrema. Okay. Then there's something called the contrapositive, where we talk about the other way. Do the opposite of what we were just talking about. And this is like an always true equivalent expression. So like if we had A goes to B, A implies B, Then the contrapositive is B goes to A. And they usually do like that. Not B means not A. So in this case, not B would be X naught is not a critical value. And X naught is not a relative extrema. I'm going to put this in the lecture. I'm going to scan it in the lecture notes. This is a formal proof of that. And it involves using the squeeze theorem. If you're interested in a formal proof of it, you can go ahead and take a read of it. It's kind of long and it like slows down the conversation. So I will include it in what I scan, but I'm not going to talk about it right now. What can we do with this stuff? So let's look at like where we have stuff that happens. So cases where we have critical points. If the graph these are all f prime of x equals 0 right now. I could have something like this. I could have something like this. I could have something like that. And I could have something like that. This is a relative max, relative maxima, or maximum. Plural is maxima. Here we have a relative minimum, plural being minima. But these two, there's no relative min or max. The slope equals 0 there for the tangent line, but nothing's going on. And then if we look at the ones where f prime of x, dne, maybe I should f prime of x naught on both of these. We could have something like this. Absolute value function. And I showed an example earlier, but we could do like these. So the relative max is there, and that's a relative max. That's a relative min, and that's a relative min. We can see it if we look at the sign chart. This is increasing and then decreasing. Here it's decreasing and then increasing. Here it's increasing and then decreasing. And here it's decreasing and then increasing. So these are the slopes. And these two, like those up there, these are not, no relative min or max here either. These are all DNEs, does not exist situations. So it kind of looks like these, and I could do a sign chart up here. The slope is decreasing here as it goes up. Let's just look at the slope. It's positive here. It's negative here. Here it's negative and then positive. Here it's negative the whole way. And here it's positive the whole way. Except at the inflection point. I didn't mean that. So I wrote this wrong. This is positive the whole way. And this is negative the whole way. So looking at these, like to the left of my pin, we have relative maxima and minima. To the right of my pin, we don't. And if we look at what's going on with the slopes, notice on the right side, the slope isn't changing. On the left side, the slope changes. Signs, it changes signs, I should say. It's changed, slope is changing. Doesn't change signs for non-relative mins and max, but for the extrema, it does change signs. So let's put that in words. In general, relative extrema occur when f prime of x changes signs. We have a couple of scenarios. A, f prime of x is greater than 0, then f prime of x is less than 0. We got something like this, followed by something like that. This is a relative max scenario. All of these will be relative maxima. And if f prime of x is less than 0, then f prime of x becomes greater than 0. So f prime of x is negative. And then suddenly f prime of x, not suddenly, but f prime of x is positive. This looks like it's the bottom. This is a relative minima. So let's look at some points. Let's just use an actual example. We'll have f of x equals x cubed minus 6x squared plus 9x plus 1. So let's find the relative extrema. If I take the derivative here, I get 3x squared minus 12x plus 9. And we want to know where that equals 0. So we can find our sign changes. I can factor out a 3. So it looks like I could divide by 3. If I factor this, this is x minus 3 and x minus 1. So I have critical points at x equals 1 and 3. Check 0, 2, and 4. Again, I'm checking them in there. 0 minus 3, 0 minus 1. This is a negative and a negative, which means negative times a negative is a positive. If I put in 2, 2 minus 3, 2 minus 1, I've got a negative and a positive. This region is negative. And if I put in 4, these are both positive, which means this is a positive region. Now, this is a slope. We're checking the slope, which means the slope is positive over here. It's negative there, and it's positive there. So this is like just without showing it changing, what a positive slope and a negative slope looks like. If you do that, it kind of helps identify the maximum and minimum. Here, we're going to have a peak right here. So x equals 1 is a max, relative max. And if I do connect these right here, x equals 3 is a relative min. I should say the relative max is at x equals 1, and the relative min is at x equals 3. the relative max value is actually what f of x equals 1 is. 1 minus 6 plus 9 plus 1 is 5. So there is a relative max of 5 at x equals 1. And the relative min, if I plug in 3, I got 3 cubed is 27, minus 6 times 9 is 54, plus 9 times 3 is 27, plus 1. That just equals 1. So we have a relative min of 1 at x equals 3. So looking at this, we can actually take advantage of concavity. This is called the second derivative test. We need f prime of x, double prime of x to exist. It needs to be twice differentiable. And we need x naught to be a stationary point. X naught is a stationary point, which means f prime of x equals 0, x naught equals 0. Option 1, if f double prime of x is less than 0, it's concave down, and we have a relative max. In option 2, if f, I should use x naught here, f double prime of x naught is, no, just x, because it's the interval. Then this is concave up, and we have a relative min. So let's put these together. Let's use a problem. Let's say f of x equals 2x to the 4th minus 4x cubed. And we want to find the relative max and min. First off, Step one, find the critical points. And then step two, either do a sign check, sign test, or evaluate in the second derivative. Okay, so we'll take the derivative. And we get 8x cubed minus 12x squared equals 0. I can factor out a 4x squared, and I have 2x minus 3 equals 0. Which means my critical points / stationary points are x equals 0 and x equals 3/2. All right, what's the second derivative look like? This is 24x squared minus 24x equals 0. If I stick in 0, I get 0, right? So this isn't positive or negative. We'll have to take a look at the sign chart to see what's going on here. If I do 3/2, this is 24 times 3/2 squared minus 3/2. Which is 9/4 minus, if I make it a common denominator, 6/4, 3/2. So this is going to be greater than 0. 9/4 minus 6/4 is greater than 0, which means it's concave up there. And x equals 3/2 is a relative min. I solve this to equal to 0. We get our critical points from solving for equal to 0. Good old algebra. Let's take a look at what's going on at 0. And we're going back to the first derivative. So the first derivative was 4x squared times 2x minus 3. I will do to the left of it is negative 10. I'll do, our other point was 3/2, so I'm going to use 1. I'm looking to see what happens around this. So if I stick in negative 10, I have negative 10 squared and 2 times negative 10 minus 3. This is a positive and a negative. This region is negative. And if I stick in a 1 squared times 2 times 1 minus 3, positive and negative, this is also negative. So the slope kept going down, but concavity changed there, which means it was negative. It was doing something like that, and it changed to that at x equals 0. That's not right.
Whoa,
That's not right at all. What's going on here? The concavity didn't change. Concavity just says 0, which means it's not a max or min. So we only had one relative point. The relative min was at x equals 3/2. We're out of time on oh shit, Tuesday's the test. Next Thursday, we'll start off with a warm-up that uses this. We'll do another example as a warm-up in the beginning. If you're interested in that boot camp, make sure you register by using the QR code, and be ready for the test. You're welcome.